prove that average velocity is the same thing as instantaneous velocity over an interval with constant acceleration, here's what you can say. So, let's think about it. Velocity over time is going to look kind of like a straight line. And what's the average value of a straight line? So, for example, starting from the origin, ending at t comma nt, where n is the slope, where is the average of this line? Well, obviously, if you use integral calculus, this is going to be very obvious, but intuitively, you can see that it should be at the value of the midpoint, t over 2, comma nt over 2. If you want to be very precise, then you can take that this length right here is t, this length is nt, so clearly the integral from 0 to t is equal to nt squared, and then you divide that by the total length of the half nt squared because it's a triangle. Then you divide by the length of this interval, which is t, to get half nt, which is exactly the value of the midpoint. So, if you have a linear velocity with a constant acceleration, then midpoint is exactly what your average velocity is going to be. So what about instantaneous velocity in this case? Well, the thing is, instantaneous velocity isn't actually equal. No, it's not. But for the specific case of the specific problem you asked about, you have 3, 8, 4, 0.
Can you draw the diagram? Right.
And you were asking, well, why is the average velocity equal to the midpoint here? Or the average velocity equal to the instantaneous velocity here? That's only because it is the midpoint. As you can see, this graph is of instantaneous velocity over time. And the average velocity is the midpoint, and, the velocity at the midpoint is the average velocity. So, there's not much distinguishing the two when you're taking a point like 3.5. But as soon as you take something like, 3.75, 6, or 3.25, 2, obviously the average velocity is 4, but the instantaneous is 6, which means it doesn't line up. So this is only true because we're working at a midpoint.